So we're on de Moivre's theorem. It's named after Abraham de Moivre, a Frenchman. We use it to find the power of a complex number. So it's very, very important. Let's use example. If you have a complex number z as our polar form, which is cos theta plus I sine theta. So let's find the power. Let's do something. Let's try and find the power z squared. We have z bar cos theta plus I sine theta all in squared. And using our laws of indices, we can split this as z squared cos theta plus I sine theta all squared. Okay, let's continue. This is settled. The first one. Okay, let's start here. This is settled. So you know this cos theta plus I sine theta is cos squared theta plus 2I cos theta sine theta, and finally plus I sine theta all squared. Yes. Which is now squared. This cos squared theta plus I 2 sine theta cos theta. Yes. Plus, remember I squared is minus 1. So we'll write it as minus 1. Y sine, this is now sine squared theta. So let's continue. This is now z squared. For our trigonometry, cos squared minus sine squared is cos 2 theta, if you remember. For our trigonometry, y 2 sine theta cos theta is sine 2 theta. If you could remember from our trigonometry, that cos 2 theta is cos squared minus sine squared. It has three formulas. It has either also cos squared minus 1 or 1 minus 2 sine squared. So these are the identity for that. Again, our sine theta, if you could remember, sine 2 theta is 2 sine theta cos theta. So this is our trigonometry. Okay, we are getting something unique here. This z squared. So let's try again. Let's find the third power. Let's try again. Assuming we are given to find z raised to power 3. Is now z that cos 2 theta plus cos theta plus I sine theta all raised to power 3. Yes, and in expanding this, we have cos 3 theta plus I sine 3 raised to power 3 plus 3 cos 3 theta sine cos theta sine I sine theta in brackets cos theta plus I sine theta. That's the expansion. If you wonder how, what did I do? I did a plus b cube is always a plus b, a cube b cube plus 3ab a plus b. It's very important. That's the formula I used here. Our a is cos theta, our b is I sine theta. So that is our cos cube 3 theta plus I sine cube I sine theta all raised to power 3. 3 cos theta I sine theta cos theta plus I sine theta. So let's continue. This is now our absolute that. So we can write this as cos cube theta. Why this is I raised to power 3. And I raised to power 3 is I squared times I. I squared is minus 4, so we have minus I sine theta. You get the logic. I squared is minus 1, so I. So minus 1 I. Plus we can split this as 3 cos squared theta I sine theta plus 3 cos theta I sine 3 cos theta I squared sine squared theta. This is z cube okay, since we have cube, we are seeing cube that, and we have sine and cos. What I have to do, we bring in, I need to come, since we have sine here, I convert cos squared to sine using the identity. And also here, convert this to cos. So I'm saying that this cos, this is at minus I sine 3 theta. So if you could remember, you can write this as I 3 sine theta. And cos squared is 1 minus sine squared theta. Yes. Why here? Remember, I squared is minus 1. So we write this as minus 3 cos theta, 1 minus cos squared theta, using our trig identity. This is z absolute 3. So we'll open up the bracket. This is I sine 3 theta plus I 3 sine theta. Remember, this is 1. So minus I 3 sine cube theta. Why this 3 cos theta plus 3 cos cube theta. So we are getting something here, which is now z absolute. So we'll collect the ones that has, okay, so we have this cos 3 theta minus cos 3 theta plus 3 cos 3 theta. See, cos 3 theta plus 3 is 4 cos 3 theta. So let's look out for cos again. Minus 3 cos theta. Why our sine? So our sine, this is cube, this is cube. Do you see it? Minus I sine cube theta minus I, that's minus 3 sine cube theta I. So we have minus 4 minus I 4 sine cube theta. That's this and this. And finally, we have plus I 3 sine theta. So from our trig identity, we can write this. Okay, this is 4 cos cube theta minus 3 cos theta. We can bring out our I. Why this is now 3 sine theta plus 4 sine cube theta. Sorry. So this minus. From this, if you could remember our trigonometry, this is now cos 3 theta plus I sine 3 theta. If you remember our trigonometry, if you could remember, 4 cos cubed theta minus 3 cos theta is what? Cos 3 theta. Y for sine. 3 sine theta minus 4 sine cubed theta is what? Sine. So what do you notice again? For power of 3, we still have 3. So generally, the Moivre is lost. We are saying that, so for any power n, it is always z absolute n cos, okay, let me use m, because we are going to do m nth root theta plus I sine m theta. So that's what we call the Moivre's theorem. So it's a very powerful theorem to solve, we use it to solve the power of any complex number. Example, if you are given, if someone asks you now, you're asked to evaluate maybe 1 minus I raised to power 4 or 8. So the only way we can solve it is to convert to polar form and use the Moivre's law. That's the only way. So this is like, if remember, our modulus is now root 2, 1 square plus 1 square root 2. I'm solving direct. Tan inverse of 1 over 1 is, remember this, if you draw the agar diagram, to 4 minus. So that's it. That's where our complex number is. So we are using the negative sense. So this minus cos pi over this pi over 4 minus I sine pi over 4. We've done it before. Raised to power 8. We just use the negative sign because this is negative. This is our actual movement. So we're now using our de Moivre's law. We don't need to waste time. This is now root 2 raised to power 8. Cos our m is 8. Cos 8 times what? Pi over 4 minus I sine what? 8 times pi over 4. So that's the importance of using de Moivre's law. So this is now 2 raised to power 4 cos pi over 2 pi minus I sine what? 2 pi. I think this is 4 times 4, 16. So 2 cos 2 pi is, cos 0 is 1. So this is 1 minus 0. Because sine 2 pi is, so the answer is 16.